our cells, recycle our macromolecules, eat up viruses, bacteria, things like that. And then they also, that's a role in the innate immune system. In the adaptive immune system, they break down whatever they digest into little chunks, and they present those little chunks on the cell surface to see if a helper T cell randomly just happens to recognize it. And it's 100% random. Okay, and then that gets into the adaptive immune system. More basophils and mast cells. So basophils and mast cells, they release things like heparin and histamine. Heparin prevents blood clotting, that's more your basophils release that, and mast and basophils release histamines, and histamines open up your blood vessels to make them more leaky, make them more open, to allow white blood cells to leave your blood and enter your actual tissues, where then they can fight off the infections. Your mast cells are non-movable cells like basophils, but they're non-movable and they're in your connective tissues. Your basophils can be more places than that. Eosinophils leave your tissues, leave your blood into your tissues, and they release antihistamines and chemicals that kill worms, like hookworm, roundworm, tapeworm, things like that. Okay, those you have all been introduced to multiple times. Like at least close to 10 times I've gone through all of that. This next one is newer. So, natural killer cells. These are cells that are only a part of your innate immune system, and their job is to go around and kill any of your cells that's infected with any virus, and they go around and kill any of your own cells that are cancerous. So, all of you and me, we have all had cancer in our body. It happens all the time. But there's two things that made it so you didn't get actual cancer and get a tumor, even though you've had cancer cells. One thing is cells are designed to kill themselves through apoptosis if they discover that they themselves are cancerous. If they keep on dividing, they activate the P53 pathway and they kill themselves. Okay? The other one are natural killer cells. They just go around and they look for cells that look weird. Cells are infected with a virus look weird. Cancer cells look weird. Your cells that are cancerous look so weird that we can just, we have a whole career. It's called a cytologist. It's a really decent job. You need a bachelor's degree plus 1 more year of training. And in like Colorado, you're looking at like 80, 90,000 a year. In Nebraska, you're looking at 50, 60,000 a year. Those are the only 2 states I know the pay because my friend who is one, that's the only 2 states she worked in. So I didn't bother to look at anything else. Anyways, what a cytologist does is like when you get a pap smear, they take the pap smear, they smear onto a slide, that's why it's called smear, and then they stain it, and then the cytologist looks at it and they identify these cells are normal and these look abnormal. If they're normal, then no one else looks at them, only the cytologist. If they're abnormal, you send it off to the pathologist, to the actual medical doctor, and then they diagnose if it's cancerous or not. So normal cells and cancer cells literally just look different. I had something else prepped, but we'll get back to that. Okay. They just look different. There's normal cells look pretty round and happy, just look normal. Cancer cells look weird. They're spiky, they stick to things. They stick to other like extracellular matrix that they normally wouldn't stick to, things like that. They just look weird. And not only can we see that with our eyes through a microscope, but so can your natural killer cells. Another one, let's look at okay, so some viruses, what they do is they put all their, I'm trying to find a picture I like. Okay, here's both ways. So, Viruses like your coronaviruses, which is COVID-19, HIV, things like that. Actually, HIV is not a coronavirus, but it's similar. It's a retrovirus. But your coronaviruses, HIV, those are the ones I know off the top of my head. What they do is they put their viral proteins onto the cell surface, the cell that's infected, meaning your own cells. The proteins go onto the cell surface, and then what happens, oh, this picture doesn't show it well. I like this picture because it's showing both things. I'm just trying to find one that I like, that trying to show what I'm trying to show. Anyways, it's not showing what I'm trying to show, but really, sometimes your viral proteins go to the cell surface, and then you insert your DNA or RNA into a little vesicle, and that vesicle gets surrounded by through not exocytosis, but the vesicle pinches off, and the virus cell membrane is your cell's cell membrane. Does that make sense? If you pinch off, I have a video that shows HIV doing it later on, so I'll get to it. The other way, you can exit through exocytosis as well, being excreted, or the third way, the cell just, once it gets infected, gets more and more viruses in it, gets so big, your own cell explodes, and all the viruses are released at once. So the vast majority of times one of your cells is infected with the virus, it will die. There's very few viruses that don't kill your cells actively. My whole point is, if one of your cells is infected with the virus, one thing, it oftentimes looks weird because sometimes there's viral proteins on the outside that shouldn't be there. And so it looks weird, and so your natural killer cells just kill them because they look weird. But your natural killer cells do not know which virus is infecting the cell. It could be chickenpox, that's the main one I'm going to use for the rest of this week, is chickenpox. The second one, below that, I'll use COVID, and then probably below that HIV, just as examples. So, but these cells do not know what you're infected with, just that your cell is infected with a virus. So, whole classes of virus, but not a specific kind. We're going to get to another cell that's very, very similar, called a cytotoxic T cell, or a CD8 cell, or a killer T cell that's like these, but they kill cells infected with one specific virus. So I'm just trying to let you know we're going to get to another cell type that's very similar. But natural killer cells, they do not know what virus your cells are infected with, just that they're infected with a virus, and they kill your cancer cells, your tumor cells, and they have no memory. So their response is going to be the same strength every time. Now to your inflammatory response. So what inflammation is, it's a cellular and chemical response to an insult or injury or infection, like you get hurt or infected, and you release chemokines to attract white blood cells to the area, and then you release cytokines to activate the white blood cells. Because your white blood cells are not active in your body at all times. That would actually kill you if they were. So I'll give you two examples of how your white blood cells will kill you. One is COVID. So COVID, and the really bad infections with like the alpha and delta strains, they're extinct now, but back when they existed, some people get something called a cytokine storm. What happened with a cytokine storm is they would overactivate their immune system so much that a bunch of their white blood cells would release a ton of cytokines like histamine. And what does histamine do? Makes your blood vessels open up, become more leaky. But if that happens throughout your whole body, and all your plasma tries to leave your blood all at once, what's going to happen to the volume of your blood? Plummet. What's going to happen to your blood pressure? Plummet, and you're going to drop below critical closing pressure, and your blood vessels collapse. And that's how a lot of people died who were infected with COVID, or they drowned in their own lungs. Both really bad deaths. Here's another example. I'll use myself, for example. One thing, I'll do two stories. So one was, I went to my wife's great-great-grandma's 95th birthday party. party. She lived to 98. Lived at home until she was 98 alone, which was awesome. She only spent the last 2 months at David Place in David City, and then she died. But anyways, we went to her 95th birthday party, and who do you think most of the people were like at this party? Old, really old. And so we were talking to them, and this one old guy just came up and started talking to my wife and I, and what's one thing old people like to talk about a lot? Because they're thinking about all the time? Their health. So he just came up to us, he was like, hey, my name's John. I have an abscess tooth. I'm gonna go to the dentist on Monday and get it taken care of. We're like, okay. And then Sunday he died. So what happened was the abscess tooth exploded and the bacteria went into blood supply. So what happens is that bacteria can go into your blood supply. Now you have bacteria within 1 minute in every single blood vessel in your body, because that's how long it takes your blood to circulate at rest. And then what happens? Your white blood cells see all this bacteria, they release histamines, same thing happens. Your blood vessels all throughout your whole body open up, all the water leaves your blood pressure plummets, and you die. I'll tell you another story of me. So, I had what I thought was a hernia. This is like when I was 24, 25. And I thought I had a hernia, but I was a student at UNMC, and at UNMC, they give you health insurance, but it's not really health insurance. What it was if you're sick, you first had to go to student health, then they would send you to real doctors. I mean, the student health they were MDs, but they were limited in what they could do for you. So you went to the student health, then they sent you on to the other doctors, and then basically UNMC, if you went there, they wrote off everything. It's basically healthcare was free. And if you're within 100 miles though, you had to go to UNMC. Otherwise they wouldn't pay for you. So I spent a lot of time in Lincoln. That was always scary. Like if I got in a car accident in Lincoln and was sent to a Lincoln hospital, I would have no insurance at that point in time. No coverage. But if you're outside a 100-mile radius, again, they just write it off for a tax write-off. So anyways, I had what I thought was a hernia. Not a hernia, sorry, hemorrhoid. I thought it was a hemorrhoid on my butthole. And so I was like, okay, and this was Saturday night. I'm like, okay, I'll wait till Monday morning when I can go to student health, because I couldn't do anything with my payment plan. Otherwise I had to pay out of pocket, and I was poor as a student. And so I went to bed, and before bed, it went from like what I thought was a hemorrhoid to like maybe that big. I'm like, ooh, that's getting big, and went to bed. 2 hours later, I woke up, that big. Go over my anus all the way to my side of my buttocks. And I was like, what the hell? It was an abscess, huge one. And I lived 1 mile away from the ER. And so I tried, it was like 4 in the morning. I tried calling my friend Liz, and I was like, can you come pick me up? But the thing is, her cell phone died and her cat's unplugged her apartment phone. So I couldn't get a hold of her. I'm like, screw it, I'll just drive my car. So I drove a little Toyota Tercel, a stick shift, without sitting down. So a tiny car by standing and driving a stick shift up to the hospital. And then got myself in, and it was a painful surgery. What it was I had a fistula, which is a tunnel, and it went around my external anal sphincter to my skin and then formed an abscess. So removing the abscess, that was unpleasant, but fine. But then what they had to do was they put a silk rope through that fistula. So basically, my butthole was pierced, pretty much, going from my large intestine out to my skin. And then over 8 weeks, it cut its way through my external anal sphincter. But they had to do that slow cutting, like it's rejecting your piercing. Like if you get one of your cartilage, if you use an ear gun instead of a hollow needle, they'll reject out. And so it cut its way through 8 weeks. It was awful. I was on Percocet and Norco a lot for 8 weeks. So, anyways, so then if I would have sat down and that abscess would have ruptured into me, I would have died within 2 minutes or so. Also, another really scary one that I've never heard of anyone actually dying from, but you can, is have you ever been told not to pop pimples in your T-zone? So that's because sometimes if you pop them, instead of going out, it can go into your blood supply. And that's also the bacteria in there, and it can give you septic shock as well. Not as big as an abscess that's big, but still it's risky. Okay, so, okay, let's go back. So, You recruit white blood cell areas using chemokines, then you activate them using cytokines. Because your white blood cells are not active all the time, for reasons I just went through. Okay, and then there's basically two ways to look at inflammation: local and systemic versus acute and chronic. So, and this is actually something I am knowledgeable on. So if we go here, if you just go inflammation, neurogenesis. It used to be the first one in Google for years, but now it's down here. This is something I wrote, and right here, right here. This is talking specifically for neurogenesis, saying that acute, short-term inflammation is good for neurogenesis. It promotes neurogenesis, secretion of new neurons. But long-term inflammation reduces neurogenesis and causes more damage. This is specific for your brain, and your brain has an entirely separate immune system than the rest of your body, but those statements are still true about your body and healing and things. So, acute short-term inflammation is always good. I have cuts all over my hand because we have a young cat at home who likes to play, and I sacrifice myself so he doesn't go after the other cats. So, anytime you get an injury, it gets inflamed, it gets red, warm, painful, we'll get to that, and that speeds up the healing time. It removes the damage, removes the infection, removes the dust, and then allows you to heal faster. Acute inflammation is always good. It allows you to heal faster, clean up the area faster. Chronic inflammation is pretty much always bad. I'll give you one example from me and one example from House, the TV show House. Example from me was I was diagnosed with Crohn's and then 10 years undiagnosed. Basically that fistula, then the abscess, the doctors were thinking Crohn's caused that, but it was actually just a random fistula caused all my symptoms. And so then they undiagnosed, same doctor undiagnosed me 10 years later. But when I first got diagnosed, he gave me a prescription to reduce my inflammation and make it not as bad. But here's the thing, I was making about, my take-home pay at that point in time was about $1,600 a month. That's what I lived on, fully. And that was enough to live in Omaha alone, in a one-bedroom apartment. But this prescription was $400 a month, and I was only making $1,600 a month.
What was it?
I don't remember. It's been way too long. I'd have to ask my doctor, to see if it was in my records.
But it was just like to help your symptoms.
Mm-hmm.
Okay.
Yep. Is it to reduce the inflammation?
Prednisone? Was that what? No.
No, I would have been okay. No, it wasn't a steroid. It was something else. Okay. And so I was like, and then it just wasn't changing my symptoms. And I was a few months in, like, dude, I went back to the doctor, like, nothing's changed, and this is a quarter of my money. Like, he was like, okay, I agree, it's not helping you, it's a waste of money, we should go off it. But he's like, I want you to understand. And he's like, I know you do understand that every time you have a flare-up, you're gonna have inflammation. And repeated inflammation, each time you have it, is gonna uptick your risk for cancer. And what's the area country with like the biggest rate of colon cancer? Like right here, like Platte County. Huge rates of colon cancer. So radon, eating too much red beef, and all the crap that's in our water from agriculture. It's like Columbus over to Iowa. That's like really bad area for cancer. Okay, so. Okay, and then just what does inflammation do? So inflammation, its entire job is to get more white blood cells to the area and to activate them. So one way it gets more white blood cells to the area is to get more blood to the area. So you dilate your blood vessels. More blood goes to the area, and what does the area, if you're lighter skinned, what does it look like? It looks redder. And then what does it feel like? Here's the thing. Next time you have an injury, and it looks red, hold up to your lips. You'll feel how warm it is, then hold up another part of your body, and you'll feel how cold it is. That's because you're bringing more blood, so to bring more white blood cells, so that brings both heat and redness, because blood's red. And then you release chemokines or histamines to open up your blood vessels, chemokines to recruit the white blood cells to leave, and then once they get into the tissue, cytokines to activate them, get them all pissed off to fight off infection. So you get heat and redness, those are byproducts, and even swelling is a byproduct of inflammation, where histamines make it open up and fluids leave. Your goal of inflammation is to recruit and activate white blood cells. The byproducts are heat, redness, pain, and swelling. Okay, and then you can get more neutrophils being produced when you have an active infection. You can get a fever from pyrogens, and then you get widespread vascular permeability due to histamines, and then, as I already described, shock can go into if you have a large infection in the blood. Okay, then here, just in general, you're gonna have some sort of damage or infection get into your tissues. You'll release chemical mediators, you'll release chemokines to induce chemotaxis, where the cells will migrate to the area. And then once those cells get to the area of damage, then you'll have cytokines that activate them. And once they're activated, then they'll do a few things. They'll fight off the infection by eating things up, removing debris. They'll also release more chemokines and more cytokines, so they recruit even more white blood cells and activate those. And then that will form a positive feedback loop of more white blood cells, more activation, more chemokines, more cytokines, more chemokines, more cytokines, more white blood cells. The more get there, they get activated, they release more chemokines, they recruit more white blood cells, and then you have more cytokines to recruit them. As long as the damage or infection is still present, the positive feedback loop will keep going, will increase. As soon as the damage and or infection is gone, then your inflammation will subside and will go away. Okay, this is going to show quite a few things like marginalization and leaving the blood vessels. I didn't talk about all this stuff. This would be things I covered in immunology class, but it's good to see it.
Inflammatory response is an important, non-specific defense against tissue damage. It begins when injured tissue cells release chemical signals that activate the endothelial cells of nearby capillaries. Within the capillaries, adhesion molecules called selectins are displayed on the activated endothelial cells. These adhesion molecules attract neutrophils, slow them down, and cause the neutrophils to roll along the endothelium. As the neutrophils roll along the endothelium, they encounter chemicals that activate integrins, which are adhesion receptors on their surfaces. These integrins then tightly attach to adhesion receptor molecules on the endothelial cells. This causes the neutrophils to stick to the endothelium and stop rolling. This accumulation of neutrophils along the walls of the capillary is referred to as margination. The inflammatory mediators released by the injured tissue bring about changes in the environment that cause mast cells to degranulate and release histamine. Histamine causes vasodilation and an opening of the junctions between the endothelial cells, allowing fluid and leukocytes to leave the capillary and enter the infected tissue. The neutrophils now undergo dramatic changes in shape and squeeze through the endothelial wall into the interstitial tissue fluid. This process is called extravasation. The neutrophils, followed by other types of phagocytes, are attracted to the damaged site by chemotactic substances released by bacteria and tissue breakdown products. They ingest and destroy invading bacteria.
So that was all innate immunity, and remember, innate immunity is way more important than what we're going to talk about next. So, because this would be overwhelmed every day without your skin, without innate immunity. Okay. Now, adaptive immunity, its main two parts is that one, it's specific, highly specific, meaning even the brand new COVID vaccine that no one is supposed to get anymore is against the new COVID that didn't exist 2 years ago. And so your vaccines you got in the past are no longer effective for that. That's why you need a new one. And viruses like COVID, actually, COVID-19 is a very slow mutating virus. All coronaviruses mutate slowly. But think about how fast they actually mutated. They had, like the alpha strain, the delta strain, and all these ones that I can't keep track of. Other viruses like HIV mutate way faster. That there will never and can never be a vaccine against HIV because it mutates so fast that it's just not possible to make one. There's cures. We've cured about 4 people from HIV, but you can't prevent it. So, you can with drugs. Like there are antivirals. So like if you are a mother who is HIV positive and you have a baby, we have drugs that make it so the chance of passing HIV on to the baby is 0%. No chance at all. None. Here. Other countries where you don't have the medication, it gets passed on. So, okay. And then so that's being specific, specificity. The other one is memory. And honestly, the memory is the important one. The fact that specific is not all that important other than it prevents like autoimmune diseases and other issues like that. But the fact that it has memory is why it's so important. Okay. And then we have antigens. Antigens, just typically think any protein. Any protein is an antigen. If your body makes the protein, then and it's coded by your DNA, then it's a self-antigen. And your adaptive immune system has mechanisms that make it so you should never ever respond to your own proteins. If you do, then you'll end up with an autoimmune disease like lupus or rheumatoid arthritis or Crohn's, things like that. But that should never happen, and it doesn't happen in most people. And then foreign antigens are anything else. Bacteria, viruses, an organ transplant, a blood transfusion, animal dander, food you consume, anything. Any animal or plant or fungus protein is an antigen. And then self-antigens we don't respond to, foreign antigens we should theoretically respond to. And then there's 2 types of immunity. In this, I also realize the general public has no idea about. I think the general public does understand that we have antibodies and that your adaptive immune system creates antibodies. That's called the humoral or antibody-mediated immunity. But there's a whole nother type of immunity called cell-mediated immunity. That's where you have cytotoxic T cells, and they go around and kill your own infected cells on purpose. But they're not like natural killer cells that kill huge classes of virus-infected cells, but these cell-mediated immunity are highly specific, meaning if it recognizes chickenpox, it's only going to recognize chickenpox. If it recognizes HSV, it's only going to recognize HSV or whatever. Okay. When our immune system forms, it forms the vast majority when you are super young. When you're an infant and a child, that's when your immune system cells are forming, and then they live the rest of your life inside of you theoretically, but they don't actually. That's why old people lose their immunity, and we'll get to it in a bit. But these cells are mostly formed in early childhood. You were all young enough they can still form. If you were 60 or 70, then they can't form. But I'm 43, you're all younger, and it can form still in you. But most of your white blood cells, your T cells and B cells, formed when you're a little kid, probably before kindergarten, probably even before you're 3. Okay, and then what you do is in your red bone marrow, you have hematopoietic stem cells that give rise to your white blood cells. And then your pre-B cells stay in your bone marrow where they mature and they become B cells, and that's why they're called B cells, is because they mature in your bone marrow. And your pre-T cells go through your blood to your thymus, that's on top of your heart, and there they mature, and that's why they're called T cells, because they mature in your thymus. Now, when these cells are maturing, or actually before they mature, when they're producing to pre-B cells and pre-T cells, their DNA undergoes a process called VDJ recombination, where they literally throw away huge chunks of their chromosomes. And then they randomly pick out a V region, a D region, and a J region, combine those together, and And you are gonna have trillions of combinations of those, and those trillion combinations of antibodies and T cell receptors are formed via VDJ recombination. They will recognize theoretically anything. Like, here's an example. When you were 5 years old, think of the year, whenever that was for you. You're all gonna be varied a little bit, but you were probably at least probably around about 8 years before COVID happened, before COVID-19, probably about 5 to 8 years before that, when you're 5. Assuming you were 5 or younger in 2013, 14. So I'm assuming a lot of you were around 13 to 16 when COVID hit. And so just think 5 years prior to that, you were older than 5. So, but the thing is, 5, 10 years before the pandemic happened, guess what you already had inside you? Helper T cells and B cells that recognize COVID-19. The decade before that virus even existed. You have helper T cells and B cells in you right now that recognize smallpox. Does smallpox exist in the world anymore? In 2 laboratories, one's in the United States and one in Russia. So we keep it alive just so we can study it if we need it in the future for something. And then, I lost my train of thought. You have helper T cell and B cells that will recognize viruses that won't exist for 1 million years from now, but you already have them. And you theoretically have helper T cells and B cells that recognize any virus or bacteria that will ever exist, and you have them in your body right now. And what's gonna happen to the vast majority of helper T cells and B cells in your body? Nothing. They will never be activated your entire life because they don't have a virus that matches up with them yet, or that virus and bacteria is already extinct. But you have the helper T cells and B cells that were formed randomly, completely randomly, but you have like hundreds of billions of these, and they form randomly. I'm gonna show you a video to go over VDJ recombination. This will show it pretty well. And then I think that's it. Oh, and then after they mature, then they go out and they go through your blood to all your lymphatic tissues, your lymph nodes, your tonsils, your malts, all things like that. Okay, here's a video on VDJ recombination.
Human cells do not have enough DNA to have separate genes for each antibody molecule. Instead, different
Okay, actually I'm gonna call it BS on him right there. Our DNA, only between 1 and 2% of our DNA codes for proteins. The 99 to 98% of our DNA is non-coding. So there is room. There theoretically could be room in our DNA for all this, but there's not. But that's not how we use it. This is more efficient.
DNA can be mixed and matched to form different antibodies. Light chains are made from V and J segments in the variable region and a constant region segment, whereas heavy chains are made from V, D, and J segments in the variable region and one of 5 different constant region segments. As the lymphocyte divides during maturation, its genes are rearranged. DNA sequences are assembled by the random selection of V and J gene segments for the light chains and V, D, and J segments for the heavy chains. The constant region of the molecule is encoded by a single C or constant gene segment for light chains and 5 different constant regions for heavy chains. The rearranged DNA in the mature B cell is transcribed into messenger RNA and translated into the light chains of the antibody. DNA sequences for the variable regions of each heavy chain are assembled by the random selection of a V gene segment, a D gene segment, and a J gene segment. The genes for the constant regions of heavy H chains have Greek letters designating IgG gamma, IgM mu, IgA alpha, IgE epsilon, and IgD delta. The DNA in the mature B cell is transcribed and translated into the heavy chain protein. The light chains are then attached to the heavy chains to form the functional antibody. Because of the large number of ways in which the genes can be rearranged, many different antibodies can be produced.
Okay, And if you actually go through the math, it's like in the low trillions of different combinations. And then total, you're gonna have like hundreds of billions of immune cells total. Or at least tens of billions. Now, if this was in immunology class, you would be responsible to know every little detail and be able to describe how this forms and everything. This is not, this is just a review, overview class. So what I want you to get from this is there's always a constant region. In this constant region, you can do things like activate complement, promote phagocytosis, promote release of histamines, things like that. You can activate your immune system. And then the variable region that's formed from the VDJ recombination will randomly recognize a single epitope. Okay, so antigens are proteins. Epitopes are chains of amino acids that are about 6 to 8 amino acids long. So your proteins are going to be made up of hundreds to thousands of epitopes. And so what happens when a macrophage eats a bacteria or virus, it not only breaks down the entire cell, but it breaks down every individual protein. And every individual protein is broken down into epitopes that are 6 to 8 amino acid long chains, and then it's presented on the cell surface on a molecule called an MHC molecule, major histocompatibility complex molecule, and that sees if your adaptive immune cells recognize it or not. And this VDJ recombination, again, is completely random, but we have so much variability that we theoretically can recognize any epitope that exists.
Human cell.
Okay, there we go. So, in order to activate your lymphocytes must be able to recognize an antigen. But they don't just recognize any part of an antigen, they recognize a specific epitope. And we have mechanisms to make it so that we are guaranteed to pick epitopes that actually make sense to use. I don't know if we'll get to it today because I only have 25 more minutes, but we'll see. But for example, if I was going to make an antibody against this remote, okay, what would I want to make it against? That button right there, or the battery? The what?
The battery.
But the problem is, it's inside. So let's think about this. Let me draw it. Okay. If I have a cell, like a bacteria, I can have a protein here or a protein here. Okay. Now I'm going to draw some epitopes. So we have this red epitope, that's some amino acids right there. And then we have this purple epitope there. Okay, and then I'm going to draw one more thing. I'm going to draw a larger, closer up protein. So here's a closer up protein. Okay, now we have an epitope, let's say here in the middle, and then here on the outside. Okay, so if we're going to have an antibody come in, I'm just trying to, here's an antibody. That's way too long on the top parts. But there is an antibody. And they bind here and here. That's really bad antibody, but it's hard to draw with my mouse. Okay, antibodies. One thing is they can't cross the cell membrane. So it would do absolutely no good to make an antibody that recognizes the red epitope because that's on a protein inside the cell. What we need to do is make a protein against this purple part because that's on the outside of the cell. But not only does the antigen need to be on the outside of the cell, but so does the epitope. Like in between this green and yellow, the green one is in the middle of the protein. An antibody is never going to reach the middle of the protein. It has to reach the outside of a protein, so it's going to bind on the yellow. So the epitope not only needs to be on the outside of the protein, but it has to be on a cellular surface protein that's embedded in the cell membrane. Otherwise, antibodies can't reach it. Okay, and then once we recognize our antigen, then what the cells have to do is they have to divide and divide like crazy. Okay, so in my personal opinion, not opinion of Central Community College or anything, is that if I had to say that I agreed in anything in life is a miracle, it would be this next thing we're gonna go through. Not birth, that's simple. Not development, that's simple. But this is crazy on what we have to go through. And I wanna introduce you to analogy first and then go through this. So, there's a movie that you're never gonna watch called Extremely Loud and Incredibly Close. It's a good movie. It came out in 2011, and it was the very first movie made about 9/11 in 2001. So Hollywood waited a full 10 years before they even mentioned 9/11 in a movie. And this is the first one they did, and it was very tastefully done. And what it was basically Tom Hanks was the dad. And Tom Hanks is in this movie for only like 5 minutes total. So Tom Hanks was the dad, and then this little kid was the son. And they played a lot of games, just like riddles and games at home. That was their way of bonding. And so the dad died on 9/11 when the towers fell. And then his son found a game from his dad, and the game was a key. It was one single key. Now, could you imagine how hard it would be if you were given one key and you were in New York City and your goal was to find the one single door or lock it unlocked in New York City? How many locks are you gonna have in New York City? Billions. And so, if you're one kid with one key, that's gonna take a long time to go and just try and find every door. So let's say we, in this room, there's like 10 of us. So what could we do if we're gonna find the one door in Columbus that this key opens up? What could we do? How could we be a little bit smarter?
Make a copy.
Exactly, make copies. So if I made this copy and gave all 9 of you a copy of the key, it would take a lot less time to go find it. Okay, so that's what your cells do. Your cells make a bunch of copies to go try to find this, because we're like going to your body and we're trying to find the needle in a haystack, but we're talking like 1 trillion cells. We're trying to find one cell out of 1 trillion cells. One. And then after we do that, okay, let's go back to the movie. In the movie, the kid found the lock that unlocked, and opened it up, and guess what he found in there? Just guess.
Nothing.
Yeah, another key. So he found another key, and then what did he have to do? Find the one lock that unlocked. And that was the movie. It was him basically trying to unlock 2 doors. So, again, what should we do after we find the second key? Make copies, and make a lot of copies. And here's something that I think I told you guys about last week. But whenever I'm sick, I always do this. I'm not sick right now. And last weekend was the first time I felt one of my inguinal lymph nodes. I'm not gonna point at it, it's in my brain. But I felt it for the first time. I'm like, whoa, that's crazy. I've never felt one in my life. So, but why do you think your lymph nodes get bigger when you're sick? Because the cells divide. And they make, one cell becomes thousands of cells. And their lymph node become bigger. Okay, so let's get back to class. Okay, so, and then they divide like crazy to effectively destroy the antigen. Okay, so what we have on cells are antigens, and each antigen has a ton of antigenetic determinants that I like epitopes here, and that's what I use that word I use. An epitope is an antigenic determinant, and an epitope again is a chain of about 6 to 8 amino acids long. And when you have 20 options for each one, that ends up being a very large number. Because 1 out of 20 for the first one, then do that 6 to 8 times. It's a huge variety. Anyways, these different antigens are on this one antigen here has different antigenic determinants or different epitopes. And when this is broken down, each of these individual epitopes will be presented on a molecule called an MHC molecule, a major histocompatibility complex molecule. So when you're getting an organ donor, the main thing you actually look at is to see if your MHC molecules are compatible. Because if they're not compatible, you'll reject that organ immediately. And who's most likely going to have an MHC molecule that's similar to yours? A very close relative. So there are cases where parents have had multiple kids just so they can hope that one of their kids is an organ donor for the first kid. It's morbid. They're basically,
I hate that.
it is morbid, but if it's a kidney, you, right now, if you have healthy kidneys, you have 6 times as much kidneys as you need. We only need 1/3 of one kidney to survive. So that's why we can donate kidneys. You still have 3 times as much kidneys as you need. So it's morbid. It's kind of, I wouldn't do it, but people do it. So, okay. This video, I like it to show epitopes pretty well.
Antigens are macromolecules, usually of molecular weight greater than 10,000, such as proteins and polysaccharides. They are recognized by the immune system as foreign. Individual antibodies are not made against the entire antigen molecule, but rather to particular chemical groups on the molecules known as antigenic determinants or epitopes. Many different antibodies can be made against a single antigen, each antibody reacting with a different epitope. Complex structures, such as the surfaces of bacterial cells, may have many different epitopes. Each different antibody binds only to the correct epitope.
And so when you do end up producing antibodies, you typically don't just make one antibody against one epitope. You're going to likely make half a dozen to a dozen different antibodies. I'm just trying to get the computer's being
Antigens
really
are
jumpy. Okay, there we go. So you oftentimes make a bunch of different antibodies all against one single foreign thing like a bacteria or virus. Okay, there are 2 classes of MHC molecules, type 1 or class 1 and class 2. We'll come back to class 1 later on, but they're basically like a little flag that says, hey, I'm infected with a virus. If one of your cells is infected with a virus, what is the fate of it the vast majority of the time? It's going to produce a bunch of virus particles and then it's going to die. So just like in a zombie movie, if you were infected with a zombie virus, what should you do immediately? Kill yourself, because if you don't, you're going to attack your family, your friends, and spread the virus. Same thing our cells do. Our cells are going to die, so it's best to kill them sooner rather than later, because the faster you kill them, the less virus particles they make. Okay, we'll come back to that. What we're going to focus more on are class 2 MHC molecules. Oh, one more thing. Class 1, those MHC molecules are found on every nucleated cell. So every cell that has a nucleus, meaning every cell in your body except for cells like red blood cells, lens of your eye, keratinocytes, the top 2 layers in thick skin, top 1 layer in thin skin. But every cell that has a nucleus has class 1 MHC molecules. Class 2 MHC molecules are only found on monocytes, macrophages, and other dendritic cells. So cells are designed to specifically phagocytize. And then that's like a rally around the flag sign saying, hey, I found this, let's go fight, let's recruit everyone and go fight this off type thing. Okay, this video I added over the pandemic because I lost all my Flash videos. You know, Internet Flash, they're all internet videos went away like 5 years ago. Like, there's a program called Flash and it went away. It was discontinued. So I lost all my videos. So when they're trying to get them, I came across this one and it shows a lot of stuff I want to show you because I used to study HIV, is about half what I studied. And then also, I would try to control my emotions by getting incredibly pissed off at this video, and I'll show you why. Not the video, it's people I get pissed off about.
AIDS is caused by the human immunodeficiency virus, HIV. This is an enveloped virus. The envelope is derived from the host cell membrane with viral glycoproteins such as GP120 and GP41 inserted into the membrane as the virus leaves the cell. The core is composed of P24 capsid protein, and the P17 matrix protein helps maintain viral structure. Inside the core are 2 identical copies of single-stranded RNA viral genome and 3 enzymes, reverse transcriptase, RT, protease, PR, and integrase, IN. To establish infection, HIV must first attach to its host cell. Attachment occurs by interaction between GP120 on the surface of the virus and the CD4 antigen receptor on the surface of the host cell. In addition to the CD4 receptor, there must also be a co-receptor on the host cell. The co-receptor differs for different host cell types. In T lymphocytes, the co-receptor is called CXCR4, whereas on macrophages, the co-receptor is called CCR5.
Okay, really quick, I want to add something in here. About 1% of humans have a version of CXCR4. That's a receptor for SDF1 alpha. It's a chemokine I studied mostly in grad school. About 1% of all humans have a CXCR4 that's mutated, and HIV can't bind onto it. So about 1% of humans are naturally immune to HIV. There are about 4 or 5 humans that have been cured from HIV. And what all happened to all of them is they all had HIV and they had leukemia. And so what they did was to treat the leukemia, they irradiated all the cancer stem cells, but when they did that, they also killed all that person's immune system throughout their whole body. So they killed all their T cells and all their bone marrow, and then they took a bone marrow transplant from someone who's naturally immune to HIV, and that bone marrow transplant went into them and repopulated their immune system. And those new T cells that are produced by the new bone marrow are naturally immune to HIV. And then the HIV has no cells to infect, so the HIV dies, and they are cured. Only about 4 or 5 people ever have been cured from that. And then there's another one that just come out with the CRISPR DNA editing technology, where they can actually go in and suck out the DNA from your T cells and cure you that way. That way scares me a little bit more than just a bone marrow transplant. So, yeah.
After attachment, the viral envelope and host cell membrane fuse, resulting in entry of the virus into the cell. Once the RNA is released into the cytoplasm of the host cell, reverse transcriptase makes a DNA copy of the viral RNA genome. As the DNA is being formed, reverse transcriptase degrades the RNA strand. A complementary DNA strand is then added by the reverse transcriptase, and the ends of the resulting double-stranded DNA segment are joined non-covalently. Treatment with nucleos...
Okay, so reverse transcriptase changes RNA into DNA. But that reverse transcriptase is highly inaccurate, and it makes a ton of mistakes. So the viruses that have RNA that's changed into DNA are called retroviruses. And what happens with these retroviruses is when their RNA changes into DNA, it makes so many mistakes, it makes so many mutations, that's why HIV mutates so quickly, is because so many mistakes are made. Even in one person, you could have multiple strains of HIV be born in one person, because they get so many mutations in different cells throughout the body. And then a lot of times, then people who have HIV will be like, oh, I have HIV, I'm just gonna go have sex with someone else who has HIV, but they don't understand they have different strains. And the different strains have a different, your antiviral proteins have different efficacy against the virus. So sometimes their HIV can go down with one strain, with one cocktail of antiviral proteins, but then the other strain goes up. And then they switch drugs, and the first strain then goes up and the second one goes down. So something that people do. I'll tell you stories. One person, she doesn't live in Columbus, no one knows who she is, but she got herpes from being promiscuous, from sleeping around. And then she wanted to date, and then she was like, oh, this sucks, I'm trying to date, but I don't want to lie. So she tells people she has herpes on the first date, because that's what you should do if you have herpes, or anything like that. And so most people would date her until she found one guy who was like, oh, I have herpes too. She was like, okay, we'll date and we'll have sex and everything. And then he got this growth on his penis, and he had HPV. So not only did then she get herpes from someone else, but then this boyfriend, long-term boyfriend, gave her HPV, and when she found out, she's like, what the hell? I didn't know you had HPV. He's like, oh yeah, I've always had that. I didn't think it was a big deal. So, now she has that, so. And that causes cancer. So, it just sucks. So, be careful.
Isn't that like illegal not to disclose for that?
Yes, it is.
Right?
So, yep, and there have been a lot of people who have had HIV and have gone to jail for deliberately infecting others and not telling them. That is illegal. But you have to report it and get it prosecuted, because a lot of crimes are just never prosecuted, right? Ever. Okay, back to here.
Logs or reverse transcriptase inhibitors interferes with these steps. The resulting circular DNA is then moved to the nucleus and inserted into the host cell chromosome by the viral integrase, IN, enzyme. The integrated viral DNA is now referred to as proviral DNA. Following integration, the proviral DNA may remain dormant, or with host cell activation, RNA may be synthesized from the DNA, yielding messenger RNA and viral genome RNA. Viral messenger RNA is translated, yielding viral enzymes and structural proteins. Some of the functional proteins are formed by cleavage of a long polyprotein by the enzyme protease. Protease inhibitors interfere with this step. GP41 and GP120 are inserted into the host cell membrane, and the structural proteins surround the viral RNA to form the core. Finally, the virion is released by budding.
Okay, so that is how your cytotoxic T cells and your natural killer cells recognize viral infected cells, because a lot of viruses put their proteins onto the cell membrane, so they can see that. Okay, so that's how HIV works. Now, this is where I get extremely upset, is go back 4 or 5 years ago, there's a bunch of people who are like, I'm not gonna get the mRNA COVID vaccines because they changed my DNA. How the fuck? I just wanted to go grab my shoulders and be like, what mechanism? How? How? There's actual mechanisms, there's real life things. There's real life situations where this stuff happens. You need reverse transcriptase and you need integrase. What is not present in the mRNA vaccines? Reverse transcriptase or integrase. So the mechanisms that allow us to insert viral DNA or RNA into our DNA doesn't exist in the mRNA vaccines. There's no mechanism. The closest one you could ever get is it does cause inflammation, and inflammation does up your risk for cancer. That's like the biggest scare from the mRNA vaccines. And that's just, but that's the amount of inflammation I get from a cat scratch. Like, it's not big deal. So, anyways, that whole idea that mRNA vaccines could change your DNA was just so silly. Like, the first time I heard someone actually thought that, I was alone, because I was teaching out of a cabin alone, because I was working remote, and I laughed out loud. I was like, how can someone be that stupid, that you think that mRNA can somehow change your DNA? But the thing is, it's not that far-fetched, though, in reality, because this thing happens in real life, but it doesn't happen with the mRNA vaccines. And in fact, you know how I just said that 99% of your DNA doesn't code for any of your proteins? The majority of the 99% is viral DNA that's been inserted into your genome for millions of years. So, just another thing. We have 4 more minutes, we'll keep on going. Okay, so. Okay, I'm just, this is.
Pathogens are processed differently, depending on whether they are.
This is being annoying. Okay, I'm gonna exit. Here's where I need to be. Okay, so. So class 1 MHC molecules, these are found on every nucleated cell. So, and I can do this in 3 minutes, so we can get through this slide. Okay, so, if you work at a factory, do they test every single thing you produce? No, they can't. Like, you can't test a needle, because you know what happens with the first time you use a needle? It gets ruined. Like, let me show you. Here's using a needle once, here's using it after 6 uses. And that would just tear through you. So it's not good. So you can't test needles, because when you test them, you ruin them. So what do we do at BD's in Columbus? You take maybe 1 out of 1,000 needles that you produce, and you test it. And if that one needle's bad, what do you assume about the other 1,000? They're bad. If that one needle's good, what do you assume about the other 1,000? That they're good. Your cells do the same thing. So every time you make a protein, you don't just make one protein. You don't read mRNA just once. You read it dozens of times, maybe even hundreds of times. You make dozens to hundreds of proteins. And then you take one of them, and you break it down, and you present it on the cell surface. If it's a self-protein, a protein that your body produced using your own DNA, you should have no T cells or B cells that recognize it, because they should have killed themselves when you were developing as a kid. After VDG recombination, we haven't got to it yet, but we'll get to it. They should kill themselves, so you shouldn't have anything to recognize as a self-protein. But who or what produces viral proteins? Can viruses produce their own proteins? No, they have to hijack a cell. They have to hijack the machinery of a cell. The cell's ribosomes, rough yard, Golgi apparatus. And so when a cell's infected with a virus, and they're producing viral proteins, they'll do what they do with every protein, take a subsample of it, break it down, present it on the cell surface, and now it's a foreign protein. And so now your cells, like your natural killer cells or cytotoxic T cells, can see them, recognize that's a viral protein, and they kill the cell. So the cell is infected with virus, so its fate is it's gonna die. So you should kill it sooner rather than later. And that's what class 1 MHC molecules are for, is they target that cell for death through things that complement. Okay, so we'll get in onto this next